We are here to help. In general, a system of first-order differential equations involves finitely many first-order equations solved simultaneously. We can write a system of first-order homogeneous differential equations in standard form like this, where x prime is a vector of first-order derivatives, A is a coefficient matrix, and x is a vector. When n equals 1, we end up with a single differential equation, which is separable, and has the following general solution. Using this as a model for general n, we can assume that this would be a solution, where eta is a vector instead of a single constant. We'll take the derivative of this assumed solution and plug it into the system. We'll move everything over to one side and factor out eta times e to the at on the right. Since exponentials are never zero, we can drop the e to the power of at since it won't contribute to the right-hand side product being zero. And we're left with an eigenvalue problem that we can solve, where little a is an eigenvalue of the matrix big A and eta is the corresponding eigenvector. We will rename little a as lambda and use lambda to denote eigenvalues. This is the general form of the solution to the system for one eigenvalue. Depending on the number and type of eigenvalues, we will have a slightly different general solution. For the purpose of this video, we will only be looking at 2x2 systems of linear differential equations. There are three possible solution types for a 2x2 system. If all eigenvalues are real and distinct, our general solution looks like this, where C1 and C2 are undetermined constants that can be found using initial conditions. The second type of solution is when there are repeated real eigenvalues, where C1 and C2 are undetermined constants that can be found using initial conditions. Eta 1 is the eigenvector associated with lambda, and eta 2 is the linearly independent generalized eigenvector. The third type of solution is when the eigenvalues are complex, which results in the complex solution, or the real solution. Let's solve the following example. First, we find the eigenvalues of the coefficient matrix by solving the eigenvalue problem. Taking the determinant and solving for lambda, we get complex eigenvalues. Now we calculate the corresponding eigenvectors. We'll call 2 plus 8i lambda 1. Plugging lambda 1 into the matrix equation to solve for its eigenvector, we get the following system. Simplifying and solving for eta 1 and eta 2, we get the following two equations. If we take equation 2 and rearrange for eta 1, we can determine our eigenvector. Since we can choose anything for eta 2, we will let eta 2 be 5. So our eigenvector is free of fractions. Now we can find the eigenvector associated with the second eigenvalue, lambda 2. Note that lambda 2 is just the complex conjugate of lambda 1, so we can expect its eigenvector to be the complex conjugate of lambda 1's eigenvector. Solving the system with lambda 2, we get the following eigenvector. Like the first one, we can let eta 2 be 5, and we get the following eigenvector for lambda 2. Using lambda 1 and 2 and their corresponding eigenvectors, we can construct the complex solution to the system. Because our original system was real, we should go further and solve for the real solution to the system. Expanding this expression and taking the real part and imaginary part, we obtain our real solution.